In the second part of this example, we're going to look at how we would determine the bending moment diagram. So to make space for this, I'm going to erase our notation from the first part. So we'll rub out this. We'll keep the nice diagram from the notes. And we can start drawing a bending moment diagram as well. So bending moment diagram. Again, we'll start off with a nice straight line because that will be our zero, our line of zero bending moment. We'll draw this across our page here. And again, this line represents the beam. So we've got these values 0 at either end to show 0, but this does represent A, B, and C. These points on this line correspond to where these forces are being applied on our beam. Now, how we tackled this in the previous example is similar to what we're going to do here, but there's a couple of things that are different which I'll point out as we get to them. So firstly, we start off by calculating our bending moments. Now, without going into it all again, we know that our bending moment to A is 0 because it's the left-hand side and there's nothing being applied to the left. And what we should have realised by now is that our bending moment at B, because there's no moments being applied, is also going to be 0. Now, we can do the maths to work this out, but we've done previous examples of this. So if you're not sure why this is the case, do the calculation to convince yourself it's going to be the case here. But the bending moment at B is 0. Our bending moment at C will calculate in the usual way. So let's take it, if we take a cross section of the beam here, have a look. Cross sections through C, and we're looking to the left of C to see what we have. So to the left of C, we've got the force being applied to A, this 7.5 kilonewton force, and it's going to be a clockwise, so positive moment relative to C, and that's going to be multiplied by 3, because that's a distance of 3 away from C. And counteracting that force at C is a UDL. Now remember, the UDL is going to be effective at half the distance away between A and C. So that's a distance of half of 3 meters. That's 1.5 meters away from C. And to work out the UDL, we look at the whole length between A and C, which is 3 meters, and multiply that by the UDL value, which is 3 kilonewtons per meter. So we're going to have a 9 kilonewton force being applied at a distance of 1.5 meters away from C. And that's acting in the counterclockwise direction for our bending moment. So we're going to subtract 3 times 3 to get our force, multiplied by 1.5, which is the point that it will appear at in terms of our calculation. And we put that into our calculator, we get a 9 kilonewton meter moment, bending moment at point C. And we can mark this in our diagram. I'll put this point here. And we'll say that's a value of 9 on our diagram here. So that's 9 kilonewton meters. And again, as in the previous example, we know that the bending effect of this beam is going to be sagging. So we're going to have tension applied at the bottom. So we plot our bending moments underneath the line. That's how we represent bending moment when we have tension on the bottom of the beam. What you will remember we did in the first example is to work out the shape of this bending moment diagram. We took bending moments at other points along the beam. So if I erase my markings here on our beam, and let's mark in 1 meter and 2 meters from the left hand side. So this is 1 meter away from A, and this is 2 meters away from A. C, of course, is a point which is 3 meters away from A, and B is a point of 4. So this gives us nice quarters of our beam. So let's consider the bending moment at these 2 points. So our bending moment 1 meter away from A is equal to 7.5 times 1, the first part, because that's the force acting at A at a distance of 1 meter away. That's this distance here of 1 meter. And we know we have to take into account the UDL here as well. So this time I'll do it in green. It applies halfway along, so half of 1 meter is 0.5 meters, and at 3 kilonewtons per meter times the distance of 1 meter. That's a distance from A to this point. So we get 3 kilonewtons per meter times 1 meter, the distance between A and this point, times 0.5 meters, the point at which our UDL has been applied at for the bending moment calculation. And if we put all of this into our calculator, what we'll find is this works out at 6 kilonewton meters. So we can plot a point corresponding to 1 meter from A on our diagram, and it'll be round about here, and we get a point for 6 kilonewton meters. Now we want to do the calculation for 2 meters away from point A. So I'll erase some of these other markings to make this a bit clearer on our diagram in the top left here. I'll erase the 1 meter, so we've got the 2 meter marking. So what we've got here is a distance of 2 meters from A, 2 meter distance here. We know that the UDL is going to be applied when you consider that, and that in our calculation we consider 1 meter away from the point we're considering this 2 meter mark. So let's put all of this in and calculate it. The bending moment at 2 meters is equal to 7.5, the force at A, times 2, because we've said we're 2 meters away from A, subtracted by the UDL force, which is the UDL 3, times the distance of being covered, which is 2 meters, multiplied by the point it applies at relative to where we're considering the moment, which is 1 meter. And putting all of that into our calculator, we get 9 kilonewton meters. And so we get a point that's going to be roughly here. This is about 2 meters along our beam. Again, this is all quite approximate. And you can hopefully see this means that we have 2 points with a bending moment of 9 kilonewton meters. Now, this doesn't mean that we have a graph that looks like this, flat at the bottom and back down. That's not what's happening here. In fact, when we have a UDL in play, rather than having straight lines joining up our bending moment diagram, we have a curved line. So what our graph is going to look like is going to be a curved line going through these points to reach a peak or a trough, I suppose, somewhere above 9, and that's between those 2 points. And we need to work out what that value is. So what is the bending moment at that point, and where that point is as well. Well, fortunately, our engineering knowledge tells us something about this. The max bending moment occurs where the shear force is 0, and that's actually indicated on the diagram notes here. So when the shear force is 0, we're going to have the max bending moment. So where is this? What is this distance x at which the max bending moment applies? Well, we can work this out, because if you remember when we did our calculation to find, for example, point C here, the in the first part, the shear force was found by taking go back and remember the shear force at C force. Shear force at C, just as we approached it, was equal to 7.5 minus 3 times 3, because that was 3 kilonewtons per meter for the UDL, multiplied by 3 the distance that C was from point A, and that gave us a shear force of minus 1.5. So that's obviously too far. That's gets a bit crowded in this diagram. I'll rub this out and circle it. So that's there. That was point C there. This is what we worked out for point C. We want to find out what's here instead. So we know this must be less than 3 meters along the beam. So how do we find it? We'll use a bit of basic algebra. What we know is at this point here, the shear force is going to be equal to 7.5, because that positive shear force at A is going to be applied, minus 3, because our UDL is 3, x, and x is this distance here along the line. And we know this must be equal to 0, because that's the point at which the line crosses. So we rearrange this, and we find that 3x is equal to 7.5, so that x is equal to 2.5 meters. So this point here, 2.5 meters, is where we have our maximum bending moment. So what do we do? Well, like we've been doing here, we just we do the calculation for bending moment at 2.5 meters. So m 2.5 meters is equal to 7.5, that's the force at A, minus 3 from the UDL times 2.5, that's the distance of beam, And then halfway between 0 and 2.5 is going to be at 1.25 meters. So this length here is 2.5. Our UDL force applied that's not very good halfway. Halfway along our beam is going to be at a distance of 1.25 meters from the point. So we put in 3 for the UDL, 2.5 for the full section of beam, and 1.25 for the point that applies that. And that gives us a value of 9.375 kilonewton meters. We can draw that on our diagram here, which gives us 9.375, and we can complete our curve there, giving us the bending moment diagram.